Hi, welcome to my video on circular orbits. So this is where we will be focusing on the idea that we have one body that's incredibly massive and another one that's small. So big M is going to be much greater than little m. So this could be like the sun and the earth and the moon, the earth and satellites. But to have a really good approximation for a circular orbit, the mass at the center needs to be much bigger than the low mass. And then in doing so, that's where we'll get a circular orbit. Not the best circle I've done, but I've definitely done worse. So the thing to remember is when we're talking about this circular orbit, this is where all the things we learned about circular motion come in. So that's where the fact that we can talk about having a radial acceleration that's equal to the tangential velocity squared divided by the radius. So we would remember that this thing's going around the orbit at a constant velocity. Because there's nothing actually constrained, there's no constraints, there's no string or anything attached. It's going to be the fact that the only force acting on this is the force due to gravity. So this force due to gravity, when the object moves to another place, it's still that attractive force towards the center. So our gravitational force is always going to be pointed towards the center of the circle, so it'll always go in this circular orbit. Now, any sort of actual orbit will not be perfectly circular. So when we're using circular orbits, we're using an approximation. And the more asymmetric the orbit is, the more we would have to then talk about elliptical orbits, which will be the next video. So circular motion, doing that. We can also remember the other things. We can talk about angular velocity being the tangential velocity divided by the radius. So we can talk about how it's going through. The reason this is actually a little bit more useful is because we can say the angular velocity is the 2 pi times the frequency, which we can also say, remember that the frequency is 1 over the period. So we have a lot of these relationships we're going to do. For the circular motion, the angular acceleration is going to be 0, which means our angular velocity will be constant. And since the angular velocity is 0, because our force is only in the radial direction, we only have a radial acceleration. We don't have a tangential or a angular. So it's just going to end up being these sort of components. Okay, so the thing about a lot of this is if we use Newton's second law, that's where we get the fact that the net force is just going to be the gravitational force. So GMM over R squared. And if we're doing this, I will say the positive direction is towards the center, positive direction. And that is going to be equal to the mass times the radial acceleration. So positive direction is pointing towards the center there. So when we look at this, and remember we can also use this definition up there, that's m times that tangential velocity squared divided by the radius. So we can take these two parts and just equate those. We'll notice that the masses cancel, and combining these, we get that the tangential velocity is going to be equal to the square root of the gravitational constant times the mass of the big object in the center divided by the radius of the orbit. So this is basically telling us that whatever distance we're at, there's going to be a certain velocity that keeps us in that circular orbit. And the further away we are, the slower the velocity is. So it's one of those things where if you're really close to it in a circular orbit, you'll be going a lot faster. The further out you are, the slower you're going to go. If you look at the, I don't have a chart for it, but if you're looking at the orbital period for the planets in our solar system, it's basically Mercury's the fastest, then Venus, then Earth, then Mars, and then I don't remember the order after that. But the further out they are, the longer their, the slower they go, so the longer it takes for one rotation. And in fact, it's one of those things where we can look at it, and we can talk about how, if we're trying to talk about one rotation, so this would be the time for 1 year on that planet, as they often say, then that's when we have our arc length is going to be the circumference, which is 2 pi r. So if we're just thinking about trying to go that distance of 2 pi r in 1 year, that's where that tangential velocity is going to be equal to that 2 pi r divided by the period. And we can use this over here to say, well, that's also equal to the square root of gm over r. So just taking the two parts over there, I'm going to say the period is equal to 2 pi r divided by the square root of gm over r. Now this isn't the clearest of way to look at it because there's r in the numerator and r in the denominator of the denominator, which actually pulls it up to the numerator. So instead of talking about it this way, traditionally they talking about squaring the period. So when we talk about squaring the period, that's going to get rid of the square root, and that gives us 4 pi r squared divided by gm over r. We have the r in the denominator, so we get 4 pi divided by gm, the whole thing times r cubed. So just kind of rewriting that, that's saying that the period squared is equal, I forgot to square pi, is equal to 4 pi squared over gm r to the cube. So again, the further out you are, the longer your period is going to be, but it's this 2/3 power sort of thing, where t squared is proportional to r cubed, or you could say that t is proportional to r to the 3/2. It's this interesting result that comes out of it, and we'll end up, when we start looking at Kepler's laws, when we're talking about elliptical orbits, this is something that's generally true. And Kepler's laws were before Newton, and basically Newton did this, and when he got this result, he's like, great, this agrees with Kepler's laws, which is pretty super awesome and great. Okay, so, all right, that's talking about, basically, this is, this page was the motion page of talking about actually talking about the circular motion, doing all that. The next part I want to talk about is energy of circular orbits. So if we're talking about energy, my personal favorite way to do it is with graphs. So we already talked about how the potential energy is equal to negative g m over r. So it will look something like this. So that's our potential energy. Now we can use what we had just done previously to say, not going to use previously. Well, I mean, I'm going to use what we just had on the last page. But if we want to know what the kinetic energy is, that's 1/2 mv squared. So when we're saying that is our kinetic energy, well, we just did v squared on our last page, and that's going to be equal to 1/2 m g m over r. Because the velocity squared, when we had the velocity, we said it was the square root of gm over r, but we're squaring it, so we get that. I don't know why I have a negative there. So our kinetic energy is 1/2 mgm over r, but if we look up here, if we're saying it, this is telling us that our kinetic energy is equal to 1/2 the magnitude of our potential energy. So if I'm to plot what our kinetic energy looks like, it's actually going to start here and go out like that. So that's what the kinetic energy of a circular orbit looks like. It's going to have the same trend, but it should always be half the value of the potential energy. And if we want to look at our total energy, well, that's going to be our potential energy plus our kinetic energy, which, as we have here, that will be negative gmm over r plus 1/2 gmm over r, which is negative 1/2 gmm over r, or 1/2 of the potential energy. So our total energy, this is where it's going to be hard. If I do it perfectly, so total energy will always be half of the potential energy. Because the potential energy is negative, the total energy is negative that half, and so it's greater in value because it's less negative, but it always ends up going through there. So you might ask, well, what if my total energy is all the way up here? If you say you have this amount of total energy, you're not in a circular orbit. So if you go through and you do a calculation and you realize that your total energy is greater than 0, then you're not orbiting. You're escaping. And in the last video I talked about the escape velocity, where when the escape velocity, we basically said our total energy was equal to 0. So if we were less than that, then we were stuck in the gravitational well. We're going to be falling, stuck inside. Same idea for circular orbits. If you have a positive total energy, then you're not going to be stuck in an orbit, and you will leave the orbit of the Earth or the Sun or whatever object you're trying to escape from. Yeah, so I think that's a cool thing. Okay, so I'm about to go off on a even more random tangent, and this is going to be talking about slowly changing the orbit. And so that means staying in circular motion. So it's going to be the idea that every change in velocity we have is going to still keep us in basically a new circular motion. And so if this is our big mass, we have our little mass, and we know that it would be, orbiting, and this, I don't know why I'm dotting, I can just, so we have that as our circular orbit, and if we want to get closer, that means r needs to decrease, which if we look at our velocity equation, so our velocity equals gm over r, so if r is decreasing to get closer, that actually means that our velocity needs to increase, which is on the side of counterintuitive because we don't think about slowly changing the motion. So the idea is that if I want to end up keeping myself in the circular motion, we'll do a zoom in. This is my rocket that's currently going upwards. In order to slowly change my orbit, I'm going to basically fire the thrusters. Okay, this is where I've now drawn this not the way I want. So I would want to angle the ship just a little bit and fire the thrusters so that I'm basically going to increase my speed and aim myself into that smaller orbit. So if I do that just a little bit of aiming myself so that it's going to move me a little bit closer to the inside and giving me that speed, that's going to get me into a slower orbit. Now, on the flip side of things, so if we imagine this as the Earth, and you're talking about an orbit that's kind of going pretty close to it, and this might be the fact that at this length, you hit the atmosphere. And so when you think about hitting the atmosphere, so like if this is our rocket going in this direction, so we have the air particles and everything that's hitting it, the net force from these particles is going to be going in that direction. So this force in this direction is the opposite of the thrust force in that direction. So this is a drag force, small drag force from the particles. So this drag force slows down and increases the radius. So when you're going at this circular orbit and you start interacting with the atmosphere, it can actually end up causing you to slow down as we would expect, but also increase your orbit. And this I've often heard referred to as skipping off the atmosphere. So it's the idea that if you're going to be going along a surface and you kind of just start to experience that drag, it actually kind of kicks you up and away. Now, what we're used to is not an orbit that's circular. We're used to orbits that just go and explode in. If you're already in an elliptical orbit, yeah, it's just going to slow you down and heat up and you're going to crash into the planet, and that's what happens. But if you're in this circular orbit and you just hit a little bit of atmosphere, it's actually going to kick you to a higher orbit. So it kind of is very counterintuitive, and that's why I wanted to talk about it. We'll talk about what happens when you're actually trying to change orbits quickly. So if we're talking about quickly, then we need to talk about elliptical orbits. Elliptical, which is the next video. So thanks for listening to my random video on circular orbits.